Hello, my name is Dr. Ritesh Ajira. Welcome to this lecture on trees. So what is a tree? A tree is an abstract model of a hierarchical structure. In this example, we have a company name, Computers R Us. In Computers R Us, we have the sales department and the manufacturing department. In the sales department, we have US sales and international sales. In the international sales, we have Europe international sales, Asia international sales, or Canada international sales. So we notice we have this hierarchical structure made up of different layers. A tree consists of nodes with a parent-child relation. More importantly, more restrictively, each node has one and only one parent. That's what makes it a tree. There are many applications of trees, such as organizational charts, an example here. In file systems, where you have a root file, it can be a folder on your desktop. Inside of this folder, you could have other folders. It could be the next layer in this hierarchical structure. If you go into one of those, you could have another set of folders. And right at the bottom of this tree structure representing file systems, you have the actual files, which could be a Word document or Excel spreadsheet. But in those cases, you wouldn't be able to click on them to find more folders. In fact, that would actually be the application. So that's an example in file systems. You also have tree structures that represent programming environments. A very famous example of this is object-oriented design paradigms. And in these paradigms, we have certain child and parent relationships between classes. So an example of this can be a superclass called animal, and different child classes from that superclass could be a class on a dog, a class on a cat, a class on a mouse, and so on. So now that you know what a tree is, let's explore the terminology we use when referring to trees. The first thing to look at is the very first node. Let's call the root node. And this is the node that doesn't have a parent. It's the only node in the tree structure that doesn't have a parent. Then you get internal nodes and external nodes. Your internal nodes are one with at least one child. That can be examples of this is B, F, C. And external nodes are those without any children. They have no children. So an example of that would be E, I, J, K, G, H, D. We then have this notion of ancestors. And an ancestor of a node is the parent of that node, the grandparent of that node, the great-grandparent of that node, and so on and so on. So for example, the ancestors of K would be F, B, and A. The ancestor of C would be A. The ancestor of G would be C and A. The definition of ancestors allows us to define the depth of a node, and that's just the number of ancestors it has. So what is the depth of F? We just count. It has two ancestors. It has B and A, so that's 2. The depth of F is 2. What is the depth of K? It would be 1, 2, 3. The depth of H, 1, 2, and so on. Well, that brings us the height of the tree. So the height of a tree is the maximum depth of any node. So you could work out that the maximum depth would be the node with the largest number of ancestors. So in this case, K has 3 ancestors, G has 2 ancestors. So the height of the tree would have to be, can be deduced from either I, J, or K, which gives us 3. That brings us to the descendant of a node. So if an ancestor is going up, then the descendants is going down. So the descendants of F would be I, J, and K. The descendants of A is everything except for A. The descendants of C is G and H. Finally, a subtree is a tree consisting of a node and its descendants. So it needs to satisfy the definition of a tree, but still has to be a smaller set, either less than or equal to the tree itself. So in this case, you have C, G, and H giving us a subtree. B, E, F, I, J, K gives us a subtree. And A, C, D gives us a subtree. Now that we know what a tree is and the different components of a tree, we can now move to defining the abstract data type of a tree. So a tree can use positions to abstract out their nodes. So in the generic methods, we have all the basic ones. How many nodes does the tree have? And it'll be the size of the tree. And whether or not the tree is empty. If the tree has nodes inside of it, it is not empty. If the tree does not have any nodes in its definition, then it is empty. So these two methods are our generic methods. We then need methods that actually access nodes. So here's one that returns the position of the root. Here's one which returns a list of positions of the tree. This will be all of the nodes. Our position-based methods can be, we dereference a particular position given to us, or one that we have called P. If we say P dot parent, this will return the parent position of P. And if we have, if we want to access the children of this position, we would just say P dot children, and that'll give us a list of positions. So you can use the position-based methods to get information about the parent and the children of a particular node. Then we have query methods. Well, this is now querying a particular position that refers to a node. So we can query a particular position and ask, well, is this the position the root? And that'll be is root. It'll return true or false. We could have p.isInternal, p.isExternal, p.isLeaf, and so on. And these all will dereference the node and tell us whether or not the node is a root, an internal node, external node, and etc. Of course, you could define many more in this abstract data type, but this is what we would expect a basic implementation of a tree to have. This brings us to the first algorithm we will apply to trees. This is the pre-order traversal. So let's begin with the definition of what is a traversal. A traversal visits the nodes of a tree in a systematic way. So any algorithm that moves from node to node, in whichever order you like, that would be a traversal. But the pre-order traversal is very specific, and it says that a node is visited before its descendants. So I like to think of the pre-order traversal in a very easy way. If you run your mouse down the tree, or in this case you run a pencil down the tree, you're going to hug the tree, right? So we're going from node to node, and we'll be moving. What I mean by hug the tree is we'll be going between each of the nodes. And what we do is we first begin by making a notch on the left-hand side of each node. So this node, make money fast, the notch will be here. And the notch for motivations will be here. The notch for greed will be here. The notch for avidity will be here, and so on. The notches will be on the left-hand side. And then we'll simply move our mouse or pencil from the root node, and wherever we intersect this node, this notch, then we would write down that node as part of the traversal. So let's begin. We'd say, we'll cut the first node here, so we're going to write down make money fast, then motivations, then this node, 3. This will be our fourth output, going down this way. This will be the next one, the next node, the next node, the next node, the last node, and we're done. This is the pre-order traversal. So one of the applications, if you have the sections and the chapter title and the sections and subsections written down as a tree structure, then you could use the pre-order traversal to simply print the sections of a document. Here's the algorithm to perform a pre-order traversal. So the important thing here is that a node is visited before its descendants, in contrast to the post-order traversal. And here a node is visited after its descendants. So in this case, you could, for example, the application here is to compute the space used by files in a directory and its subdirectories. And we can do this since we are visiting nodes after its descendants. We can calculate the amount of space for each of the nodes before a higher level in this hierarchical structure, and simply keep pushing the sum up until we get to the root. So in a post-order traversal, instead of making the notch on the left-hand side of the node, we're going to make it on the right-hand side of the node. And we're going to move our arrow, or we're going to move our mouse or pencil and hug the tree, and wherever we intersect the notch, that will be where we output the node. So we'll output this first, and then this next, and then homeworks going down, then ddr.cpp, then stocks.cpp, then robot.cpp, then programs to do.text, and we make our way back to the root. And this is how we would perform the post-order traversal. Alternatively, you could remember the algorithm, which is post-order v, and then for each child, this is just saying that we are visiting a node after its descendants, and it's a recursive definition. Note where the visit is. Before, the visit was on top, before we visit the nodes, and now it's at the bottom because we're visiting after exploring the descendants. Okay. This brings us to the notion of binary trees. So before, we could have as many children as we wanted to. So looking at the previous trees, you could have this node has 3 children, 1, 2, and 3. Methods has 1, 2, and 3. Motivations has 2. But if we restrict the number of children to 2, see, like programs here has 3 children. If we restrict the number of children to 2, then we begin binary trees. And binary trees is a very common and very powerful concept in computer science. It's used for many interesting problems. So a binary tree has the following properties. Okay, each internal node has at most 2 children. At most 2 children. You could have 1 child. But if it's a proper binary tree, then you must have exactly 2 children. And the children of a node are an ordered pair. What do we mean by ordered? We mean that where the position of the node matters. The position matters. So in this case, B is on this side of A and C is on this side of A. So B is A here is the root, B is the left child, C is the right child of A. D is the left child of B, E is the right child of B, F is the left child of C, and G is the right child of C. This is important. The order of the children matter. There is also a recursive definition for tree, which I can leave you to explore. So what are the applications of binary tree? Well, we could use them to compute arithmetic expressions, where we represent the expressions as a tree, where each node would represent the internal nodes would represent the operand, the operator, and the external nodes would be the operand, which is the number. And in that case, you can, if you perform either pre-order or post-order traversal, you can actually compute the sum or the whatever the expression is. You can also use it for decision processes, where you start off at a particular node A and a robot needs to make a decision, either go left or right, or eat the soup, or throw it out the window, or move its arm in a particular way. These decision processes can be represented as trees. We also use trees for searching, and we find that binary trees are particularly useful in searching, and it does this in many ways, which we will explore later on in the course. So here's an example of how we could use a binary tree to perform an arithmetic expression. So here we have an expression 2 multiplied by a minus 1 plus 3 times b. Well, we could have our operator plus as the root of the tree. This part will go on the right, this part will go on the right of the tree, this part will go on the left of the tree. And we find the middle operator here, which is the multiplication. The multiplication goes here, 2 moves to the bottom. This expression goes on the right hand side of the multiplication, which would be here, and we split this up again, and we also split our 3 multiplied by b on this side. And if we do that, we would have our operators as the internal nodes, and we would have our operands, which is the numbers, or in this case a variable, would be the external nodes. We also refer to the external nodes as leaves. So if you hear me refer to it as a leaf, don't panic, it just means an external node. So here's another example of a decision tree. The decision trees are very popular in artificial intelligence, so if you are interested in AI, you'll be interested in something like this. So you can always think about a robot making decisions in an environment. In reinforcement learning, this is very common. And here you have an environment, and then you have different evaluation functions, and basically in that environment, the robot needs to make a decision based on certain contexts. And the way it makes those decisions, it follows a finite set. The search space is finite, and it moves from one state to the next based on the decisions it makes. So here's an example of one. Well, if you want a fast meal, then you can have a coffee. If you don't want a fast meal, then you can have something more expensive, and so on. And you can continue in this way. Moving down to a leaf, which would be the actual decision. Well, now that we know what a binary tree is, well, let's look at the properties of binary trees. And the reason why binary trees are so popular in machine learning, in formal language, in automata, in Turing machines, and many other places, the reason why they're so popular is because binary trees have some beautiful properties, and that's what we want to discuss in this slide. So let's begin with some notation. Well, let's begin with a definition first. Well, what is a binary tree? If you remember, a binary tree is a tree that has at most 2 children. So a proper binary tree is a little bit different. Here we say every node has to have either 0 children or 2 children. A node can't have 1 child. So you'll see at the bottom there's some examples of proper binary trees. So this is a proper binary tree. Each node has 0 or 2 children. So this one has 2 children, this one has 2 children, this one has 2 children, this has 0 children, 0 children, 0 children, 0 children. 0 children, 2 children, 2 children, 0 children, 2 children, 0 children, 0 children. I'm looking at the notation. N here on the slide will be the number of nodes. E is the number of external nodes. I is the number of internal nodes, and H is the height of the tree. And remember, the height of the tree is the number of ancestors. So the height of this node is 2. The height of this node is 3. The height of this node is 1. The height of the root is 0. Okay, but the height of the tree, remember, is that the maximum height. Okay, in other words, the maximum depth of a node. So in that case, the height of this tree will be 1, 2, 3. The height of this tree will be 1, 2, and so on. Okay, so let's look at the first property. The first property is that the number of external nodes is equal to the number of internal nodes plus 1. And that makes sense, because remember that the external nodes, if you think of a generic tree like this one, then the external nodes would be the ones at the bottom, the last layer. And we're saying that that's equal to all of the internal layers. So it's the layers inside. So for example, all of the nodes here plus all of the nodes here, and if we add more layers, we'd keep adding our number of internal nodes. So if you think about it that way, then the number of external nodes, which is right at the bottom of the tree, the last layer, is equal to the sum of all of the other layers plus 1. Alright, in that case, we can also define as the number of nodes, n, is equal to 2 times the number of external nodes minus 1. A nice way that you could actually prove this is you can remember that the number of nodes in the tree is equal to the number of internal nodes plus the number of external nodes. So that's n is equal to I plus e. If you substitute, if you rearrange this formula, you're going to get I is equal to, you're going to have I is equal to e minus 1. Okay, you're just going to move this 1 to the other side, so it's going to be I is equal to e minus 1. Then you can substitute your I is equal to e minus 1 into your n is equal to I plus e. And if you then simplify that expression, you'll get this. So that's a nice way to remember how to prove this expression. And that's what I will ask you in exam-like questions. I'll ask you to deduce certain properties. I'll give you a property and I'll ask you if this is a property of a binary tree. And all you would need to do is remember some of these and then use them to try to deduce whether or not the property is valid. So in order to show you the next property, I've stuck in a full binary tree with just one more layer, just so we could see how this would work if we unfold this a bit more. So in the next property, we have h is less than I. Now remember, h is the height. In this case, this full binary tree, the height is 3. And the number of internal nodes, let's count them. This is 1, 2, 3, 4, 5, 6, 7. There's 7 internal nodes. So h is definitely smaller than I in this case. So you can prove this one inductively. You can say, well, okay, let's start with a single node, right? It's going to be 1. And it's going to be one node. And if it's just a node alone, you would have the height would be 0 because it would have no ancestors. Okay, and in that case, there is a node, so that 0 is less than or equal to 0. You could say that it's an external node. In the case of 2 nodes, so you have the root and then either a left or a right child. In that case, you have the height is 1 of the tree, and since there's 2 nodes, one internal and one external, you would just have those 2 nodes, so it will be 1 internal. So in that case, your h is 1, your I is 1, and so h is less than or equal to I. And you can increase it this way, and you'll see that this always holds true. And this is inductive proofs, right? Okay. I'll leave you to figure this one out on your own. Bear in mind that you can use this property to deduce this property. All you would need to do is find the definition of I, which equals to this. Or it doesn't have to equal, it can also have the same less than equal to relationship, because then you can just use the trichotomy rule. So you could definitely prove this one. Okay, great. The next property is that the number of external nodes is less than or equal to 2 to the power of h. And before we discuss this property, we need to consider what's actually going on in this full binary tree. So have a look at this full binary tree. Let's try to define the number of nodes in the first layer. The number of nodes in the first layer is, well, let's just use, so we're using 2 because there's 2 children, so it's equal to 2 to the power of 0 gives us the number of nodes in the first layer. So 2 to the 0 is 1. Right? Then we have 2 to the 1 for the next layer, that gives us 2. For the third layer, it's 2 to the power of 3, which is 4. 2 to the power of 2, which is 4. Then we have 2 to the power of 3, okay, to give us the next one. If you can guess, the next layer will be 2 to the power of 4, then 2 to the power of 5, and 2 to the power of 6, and so on and so on. So, we can easily say that the number of external nodes is less than or equal to 2 to the power of h in this case, because that would be in this case h is going to be the height of this tree, which is 3. So we're saying in this case the number of external nodes, which is this layer, is 2 to the power of 3. Okay, and that'll give us the number of external nodes. Well, we would say that'll be exactly the number of external nodes, but maybe this node in another tree doesn't have any children, in which case it would be less than 2 to the power of 3. So in a full binary tree, we could say that the number of external nodes is exactly equal to 2 to the power of whatever h is. In this case, it's 3. But in the case where we don't have a full binary tree, or we have a proper binary tree where perhaps this node doesn't have any 2 children, then we could say that e is less than or equal to the upper bound, which would be 2 to the power of h. So then how do we get this? Well, this, if you look at this expression, if we just take the logarithm of this, okay, well, we get this. Then our h will be greater than or equal to log 2e. And I will leave you to get this last one. And it's not much different. You're just substituting e we're just substituting e. But bear in mind that you can represent the number of internal nodes with respect to the number of external nodes. And you can say, in this case, the number of external nodes will be 2 to the power of 3, right? And to represent the total number of nodes inside of the tree, the total, because that's what this expression does, right? It's representing the total number of nodes with respect to the height of the tree. But in that case, you can represent the total number of nodes by simply doing this. You have 2 to the 0 for the first layer, 2 to the 1 for the second layer, 2 to the 2 for the third layer, 2 to the 3 for the fourth layer. And you would remember, okay, because we're doubling in size all the time, if you had to compute the number of nodes for the next layer, it would be simply 2 to the power of h plus 1. 2 to the power of h plus 1. And taking the logarithm of that will give you this expression. And that gives you a representation for the number of nodes and the height of the tree. So this is important, and this is what I like to test in exams. The third traversal algorithm I'd like to teach you is the in-order traversal algorithm. And in this traversal algorithm, unlike the pre-order traversal, which visits and then goes to the left child and then the right child, and the post-order, which goes to the left child, right child, and then visits the node, the in-order traversal, which only makes sense in binary trees, it visits first the left child, then it visits the node, then it visits the right child of the node. Okay, and the way you would visualize that in this context, before the pre-order traversal, we make the notch on the left-hand side of the node. The post-order, we would make the notch on the right-hand side of the node. While in the in-order traversal, we make the notch at the bottom of the node. So if we're going to make a notch at the bottom of all of the nodes here, and then traverse our algorithm, or we'll traverse our tree, we're going to go this way, we'll cut the first notch here, then this will be the first one we visit. And then we would visit 2, and then we would go to this node, which will be 3, then this node will be 4, this node will be 5, this node will be 6, this node will be 7, 8, 9, and we're done. So just you can use these notches to help you, but you should remember that in an in-order traversal, a node is visited after its left subtree and before its right subtree, which is exactly this algorithm over here. You can see it looks at the left subtree first, then it visits the node, then it looks at the right subtree of that node. Now this is very useful for printing arithmetic expressions. So if you got your arithmetic expression represented as a binary tree, as you can see in the example on the bottom left, then you can simply use an in-order traversal to print the expression. So you would print the expression and you would get this. You can see then first the 2 will come out, which will be this, then you will have the multiplication, then you would have the a printing out, then the minus will be next, then the 1 will be after that, then the plus will be after that, and then the tree, then the multiplication, then the b. But what's interesting is that where do these parentheses go? So you can figure that out. Yeah? Where do you think the parentheses will go? And, or more interestingly, can you derive an algorithm that puts those parentheses in the right place? And I'll give you a clue. You can use when this traversal algorithm goes up and down, perhaps you can assign some kind of routine, subroutine that prints parentheses in a special way. Yeah? And perhaps you could use the fourth traversal algorithm to help you with that, which we will see in a few slides. So evaluating an expression, well, we could print an expression very nicely with in-order traversal. We can also evaluate arithmetic expressions using these traversal algorithms. And in this case, using the post-order traversal, we can actually evaluate expressions. And here's the pseudocode on how to do it. It's a very nice algorithm, and you can try it out. To evaluate an expression, you can say, given a node, is it external? Or else you would have the first number, which would be the left child, the second number, the right child, and then the operator would be the node itself, and then you would just simply return the evaluation of that subtree. So this would be this example of the subtree. Then the subtree would compute, the subtree would compute, and so on. Now you can run this algorithm on your own and trace it and see if you get the right result. The last, which is the fourth traversal algorithm, which I'll teach you, is the Euler traversal. And in the Euler traversal, this one, it visits everything. So it visits, if you make a notch for the Euler traversal, you would have to make a notch all around the node. You would make one on the left-hand side of all of the nodes, the bottom of all of the nodes, and the right-hand side of all of the nodes. And in that case, you would be going wherever you cut a notch, no matter where it is, you write it down. So if we have to perform a Euler traversal on this tree, we'll print out the plus, then the multiplication, then 2, 2, 2, because there's 3 notches on 2, so you print it out 3 times. And then the multiplication, then the minus, then 5, 5, 5, minus 1, 1, 1, minus multiplication, then the plus, then the times, 3, 3, 3 times, 2, 2, 2 times plus. That's an example of a Euler traversal. So it's simply walking around the tree and printing out all of the nodes you touch. Can you think of a way of using one of these traversal algorithms, and maybe you could use the Euler for this, to deduce the height of the tree? And then think about how you would find the max element in an array. So if you're looking at an array and you want to find the maximum element, what do? You save the maximum. So can you think of an algorithm, devise one, where you compute the height of the tree, which, you remember, is the maximum number of ancestors for any node. So that would be the maximum depth of a node using a Euler traversal. See if you can do it. And perhaps, just to give you a clue, for each of these, you keep a counter that monitors when you're going down the tree and up the tree. And that counter, either it does something to it's a variable, it does something to the variable. Perhaps I feel like I'm solving this for you, but you can actually add something to it when you're going in a certain direction and subtract from the counter when you're going in another direction. And by doing that, you can actually solve this problem. And then try to think about this in terms of algorithmic complexity. What is the complexity of this? If you solve it in this way, what is the complexity? And remember that you have a finite number of nodes, so you can deduce the complexity. And you might be surprised, it might be constant to deduce the height of a tree, which is fantastic. Remember, the only thing better than constant, well, there's nothing better than constant. The O1 and OC, OK is all, C and K are real numbers. It's our integers. These are all constants, and the computer is very happy with algorithms that are in constant time. So there are many ways you can represent a tree structure in a computer, and we'll look at 2 ways, one using linked lists and one using arrays. So the first way here is the linked list way of representing trees, and in this case you define a node that has an element, a parent node, and a sequence of children. So here's the element, this is the parent node. In this case, remember, a tree has one and only one parent for any node. In this case, since there isn't any parent for B, then we wouldn't have, it would be empty, right? And B is the only one without a parent here. So yeah, and the last part of the node is a sequence of children. Again, this in itself can be an array, a linked list, or whatever you'd like. So here you have a pointer to a sequence of children. Well, the sequence of children, if you dereference them, it'll give you A, D, and F, which are the children of B. A points back to B because it's a parent, and it has no children, so that set is empty. Right? See, A has no children. D has a parent B, so it points back. F has the parent B, points back. D has children, so it has its own set of children here, and which are C and E. Right? It points to C and E. This is the one where you can represent a tree. If you want to represent a binary tree, then you don't have to represent a sequence of children. You can just represent 2 children. So you got the parent node, you got the element, you got the left child, and you got the right child. And that will be an example of a node in the node class. And in there you have B, which is the parent, which is a node. B, it has no parents, so this would be empty. And this points to the left child, that points to the right child. A has the parent B, so it points up. It has no left child, no right child. D has a parent pointing back to B. D has a left child, it has a right child. C has a parent, which is D, has no left child, has no right child. E has no left child, has no right child. This is another way of representing. This is also using a linked list, but it's using random access, just as linked lists do. But this is specifically for binary trees. So we don't have a sequence of children. Rather, we have either a left child or a right child. And that brings us to the array-based representation. So those were random access representations before. That was using linked lists. But now we're using array-based representations, which is contiguous memory, which means that the items in this tree are next to each other. In memory, they're next to each other. So the nodes are stored in an array which is contiguous, and that will be A, B, D, and so on. So let's see, how do we actually deduce this? Well, to get the left child, we'd have 2 times the rank, okay? And to get the right child, it'll be 2 times the rank of the parent node plus 1. So A would be 1, okay? Where do we put A's left child? Well, we would have to put it, like we say it here, 2 times the rank of A. So if A is 1, it'll be 2 times 1, which is 2. And that's where we'll put the left child. So B goes here. The right child will be 2 times 1 plus 2 times 1, which is the rank of A, plus 1, which gives us, it's this formula, we'll get 2 times 1 is 2, plus 1 is 3, and then the 3 will come here. Where do we put B's left child? Well, B's rank is 2, so 2 times 2 is 4. Then we're going to put then E at position 4, so it will come here. And where will we put its right child, F? It would simply be 2 multiplied by 2, which is 4, plus 1, which gives us 5. And then, so at rank 5, which would be the index, if you want to think of it as index, you can, because this is an array, then you would put that, you put F at rank 5. And you can now fill the rest in. Well, what's wrong with these representations? Let's just quickly discuss that. Well, in the random access representation, we weren't wasting so much of space, okay? Because we would have nodes, we could be scattered throughout memory, we had ways of getting to them, but we did have a constant amount of space that we needed for each of the nodes. Okay, so we could think about here accessing nodes. We would need, for example, if you want to get to E, right, and we only have the root node, we would have to go from, we'll have to get to E by getting to, we have to go to B, then go to D, and then get to E. Okay, so we have to take this route. Notice that in contiguous access, you can dereference E much quicker. But the biggest problem with the array-based representation is that if we don't have full binary trees, if we have trees, perhaps a tree that is just like a linked list, let me show you one, a tree like this, one that just keeps going. So you just have a right child of a right child of a right child of a right child, on and on and on 15 times. Then you'll see that there'll be lots of empty blocks in this array-based representation. And that could be a big problem, because remember, if we are doubling in size, the number of space doubles. And that means the number of blocks that we need to represent the next layer doubles too, which means we are wasting space. And wasting space in this way is terrible for computational complexity, although the time complexity is really good here. The space, because you can access elements of the array in constant time, the space complexity suffers tremendously. And I hope this video was not too long, but thank you for